Alright, Locus problems. So we've got the formats of the different types of Locus depending on certain conditions for the complex numbers. So we've looked at lines, looked at circles, and we've also looked at rays. So what we're going to do is apply some of those techniques today and also use some algebraic methods to work out the varying Locus for the following criteria. Right, first one, I'm going to illustrate the following reason Argand diagram. That negative pi on 6 is less than or equal to the arg of z take away I, which is less than or equal to pi on 6, and the absolute value of z take away I is less than 1. Right, so what do we remember about the argument? Locus of an argument. It's a ray. Okay, so we've got pi on 6 and negative pi on 6, and the argument, the region of the argument is, is between those two rays for those two arguments. Okay, so the centre, so we've got the argument of z take away I, so the centre can be an open circle at I. Okay, so we can't have an argument of a point, we need to have some form of line, so therefore the starting point is undetermined. Alright, so 30 degrees, pi on 6 is 30 degrees, so I'm going to branch out. Sorry?
What is it 30 degrees from?
In what?
Is it from the imaginary axis, the 30 degrees?
Yeah, from the horizontal. 30 degrees to horizontal. Yep, because we shifted the centre. Okay. That one, yep. Okay, so there's the argument. So 30 and negative 30 with the horizontal in degrees. Okay, so we've got less than or equal to components. So we've got the unbroken line. And the absolute value of z take away I is less than 1. So what do we remember about the locus of an absolute value? No? Well, yes, in normal, but we're looking at complex numbers. Thinking about the modulus. So when we take the modulus, we're finding the radius of the circle with the modulus, okay? So the centre at the same point with the centre of the argument, okay, and it's less than 1. So that's the radius. Okay, so the same centre, radius is 1. Okay, so we've got the centre 1 unit up, therefore the radius is going to touch the origin. Now we need to illustrate the region. Alright, so the argument is between those two rays because of the condition there, and the modulus of that circle is less than 1. Okay, so the modulus, is less than 1, which produces a circle. So it's going to be within that circle and within those two rays. Okay, so that is your region, that sector between those two conditions there. Okay, you can shade the whole region in here, then shade the whole circle, then shade the common region, like we've done in mathematics. However, that's a basic skill compared to what we're doing now. Alright, so as long as you're showing the correct region, that will be sufficient enough for that. Alright, any questions on the approach? Right, find the locus of omega if omega equals z take away 1 over z, given that the modulus of z is equal to 2. Right, so the first thing we're going to do is get Z the subject of that equation. So omega Z is equal to Z take away 1. So I've got Z subject there. And the reason why I need to get Z subject is because I am given a condition for Z. So I've been told that the modulus of Z is 2. Okay, so in other words, the absolute value of Z, Z's that, so we take the absolute value of that, and we know it's 2. Right, so in other words, 1 over the absolute value of omega take away 1 is 2. And then I'm going to make omega take away 1 the subject of that equation. Okay, so we're going to swap those two over. So omega take away 1, the absolute value, is going to be a half. So, what is the locus of the absolute value, or the modulus of omega take away 1 equals a half? Hey? Well, when you're taking the modulus, what's the locus in general? Circle. Okay, so take the absolute value, alright, and give it a half. Okay, so in other words, okay, centre at omega and radius half. That was the rule that we looked at yesterday. So therefore, locus, yesterday, last lesson, locus is a circle, centre at 1, 0. Okay, so the centre is the omega is just 1, it's just the real part of it. Okay, and the radius is a half. Okay, so when you're given a condition for your complex number, so here the absolute value Z is 2, you need to get that subject of the equation and then use the condition to finish off the question. Okay, so that's the locus. So it's a circle, centre at 1, 0, and the radius of a half from there. Now I think I've added this one to your notes. So I've said imaginary, so I'm also going to include the real part as well. Okay, so the next question is the imaginary. So if omega is purely imaginary, so we're going to look at real first. So just an added question to that. Alright, so let z is x plus yi. Don't know why that dot there. Not supposed to be there at all. Okay, so omega is z take away 2 on z. Okay, so we've got omega is going to be x plus yi take away 2 all over x plus yi. Right, so we're going to have to rationalise the denominator, okay, to help us further on with the question. Okay, so I'm going to multiply by x take away, so multiply by the conjugate. Just going to tidy up a bit first. The x take away 2, that's the real part, and then the imaginary part. And then I'm going to expand it with x take away y. So I've just grouped the real parts of the complex number and the imaginary part on this side, and then I'm going to multiply by the conjugate. Okay, x squared plus y squared. On the bottom, when you expand that out, right, so we're going to use the FOIL on the numerator to expand all that out, and then we're going to factorise into real and complex part. Right, so x x outside of x take away 2, so first minus right, and the good thing is, with those two cancels, it helps. Right, so just group the real part from the left hand side. Just group the real part from the left hand side and the imaginary part on the right. Okay? So we followed that, what we're doing there. So we're given that omega is purely real. Okay? So if omega is purely real, any suggestions on what you know about the whole complex number? Say again, sorry? Okay, before you go to that stage, what did you do first? isn't the imaginary part of omega equals 0? Okay? So if omega is purely real, that means that the imaginary part must be 0. Okay, so in other words, 2y over x squared plus y squared must be 0. Okay, so in other words, 2y is 0, y equals 0. So we've got the real axis. But is there any limitations on that equation here?
Is it, I know that if you can,
Yep.
on the bottom, if you do it along, and then you can manipulate the equation another way and it'll give you a different answer. It's like
Yep.
an asymptote or something. Something like that. We learn it in prelim, like in prelim. Is it one of those equations you can manipulate two ways and you'll get two different answers and it'll give you like a limit or something?
Okay.
I don't remember.
Hey,
Is it a locus?
it is. But the locus is the line. But why do they exclude the point 0, 0? So yes, you're right about the concept of an asymptote there. But it's not going to be an asymptote because the line is not going to approach the asymptote in this particular example. Okay? So why does it exclude the point 0, 0? We cannot have a denominator of 0. Okay, so the locus is going to be the horizontal line y equals 0, in other words, your real axis, but it has to exclude the point 0, 0. Okay? I hope that's correct because I'd done a different example and I forgot to redo this one, but as far as I know, that should be fine. I'm happy with that. Yep. Alright, so got the line, so therefore locus is the line y equals 0, excluding the point 0, 0, since the denominator cannot equal 0. Alright, so this is what's in your notes. So given that omega is purely imaginary. Okay, so from C. Okay, so it's the same equation. So we've got that bar. X squared over 2x plus y squared. Is that right? Right, So from that, okay, so that was the tidy up, okay. So if omega is purely imaginary, okay, what can you tell me about the general complex number omega? If it's purely imaginary. Yep. Okay, so if omega is purely imaginary, then the real part of omega must be 0. Okay, so x squared take away 2x plus y squared over x squared plus y squared has to be 0. Okay, but the condition, again, so x squared plus y squared cannot equal 0. Okay, because we cannot divide by 0. Right, you've got to keep these things in mind. So, if I were to cross multiply, that's fine. Okay, so x squared take away 2x plus y squared is 0. Alright, so I've already considered what's happening in the denominator, so I can't have 0. I'll fix it up in a moment. So what is this equation provides the graph of what? Nope. Yep. If it's a parabola, one of these variables has to be the power of 1. You can't have x squared and y squared and a parabola. Yep. Alright. So, I need to find the, so I've shown it's a circle. I'm going to find the radius and the centre point. Okay, to finish off the full statement of my circle. How am I going to do that? Synchronise yawners. It's quite a spectacle. What did you say first, show?
X is factorised 2x with x squared, so it will either be plus or minus 2. I can't remember.
So x outside of x take away 2, is that what you're saying?
Sorry.
X outside of x take away 2, is that what you're saying?
I'm grouping them together so it's like a circle formula.
Yeah, so how are you going to do that though? Alright, x squared take away 2x plus y squared. You have to complete the square. That half and square. Include it on both sides. Okay. So therefore, locus of omega is a circle, centre 1, 0. Hey?
I spelled circle with an E instead of an I.
Okay, now you've got to be careful. X squared plus y squared equals r squared. Okay, just like back in mathematics, extension 1, so the radius is r squared is 1 squared. Okay, so the radius is 1, doesn't matter in this one, but if it was 4 here, the radius is 2. Alright, you've got to be careful with these things and not get confused about when you have the locus of z take away omega. Is r is the radius, not r squared or anything like that, so you've got to be careful. Alright? Yeah, no. A lot. Okay? Centre, circle, radius 1. Okay? And of course, that circle, the circumference, would go past the origin, wouldn't it? Because of x squared plus y squared becoming 0. Okay? So, except radius 1 excluding the point 0, 0 as x squared plus y squared cannot equal that. Right. So it can be quite in depth, okay? I will admit I got a bit nervous when doing some of these questions. Not too bad, okay? But there might be some questions that might be more of a hair pulling out experience for you, okay? And we'll see how we go.
That would be awesome. Thank you.
That's right. Now there is one more question that I still haven't got my head around, so I'm not going to go through it today.
Let's do it.
Let's do it.
We can collectively get our heads around it. No, we can't.
I've got most of it, I've just got that final bit I need. I can't get my head around why it works. I can start it and we'll just have to finish up the last bit.
Inside's going to be 45
We'll
degrees.
finish it off what you're on your head.
Something to do with conjugates. That's all I saw.
Alright, I'll make a start and we'll see if we can make some progress in an extra bit of information you need. Alright, let's try this and you might be able to make some insight on what's going on. Alright, so let capital A is 1,
6.
B is -1, and point P is going to represent by the complex number Z. Okay, because of the argument, centre at 1 and -1 for the two arguments there. Okay, so there's your real axis, there's your imaginary axis. So, A and B, the centre for the two arguments. Okay, so it's represented by A, B. Okay, and then you have some point P that makes a locus. Alright, so I'm going to make P up there. Right. Now, the argument, so the argument there for Z take away 1 is going to be represented by that line, that interval, sorry. And the argument from B up to that point is going to be that line there, just put on the table there.
I got room there. But it was what?
Okay, so this is the argument made by there. This is the second argument, okay, from the horizontal axis up to the interval, okay, that it meets the common point P that subtends the angle on the chord AB of pi on 4.
So that angle.
Sorry, go ahead, check.
BPA equals pi on 4.
Sorry?
BPA equals pi on 4.
Yes, yes. Okay, that's what I'm saying. I'm not fully understanding the solution, okay? But like I said, if I take it through, I'll get most of it, just this final bit, okay? So, the argument of Z take away 1, the arg Z take away 1 is the angle the ray from 1 to Z makes with the horizontal, okay? So, it's going to equal angle P A with the x direction, okay? So angle PA to the positive x direction, okay? That's the angle that makes, okay? And the arc of Z plus 1, okay, is the interval from -1 to P with the horizontal, and that's angle PB in the remaining x direction. Okay? Now, mathematics. That plus that equals that, doesn't it? Okay? So therefore, angle PAX take away angle PBX is pi on 4. Going a subtraction. So if that plus that equals that, Therefore, that take away that must equal that. Okay, exterior angle result. Okay, so the locus is an arc. Okay, so you think about it, if that is always pi on 4, this angle between the two modulus is always pi on 4, as you circulate that around, it's going to follow an arc of a circle. Alright? However, my trying to reason and think about this, I wasn't quite able to determine the centre and the radius of this circle. Alright? So the locus is an arc, that's a 10. An angle of pi on 4. On the chord AB. Okay, with the points A, B and P forming a circle. Now, there's actually one thing I forgot here. Again, we can't have the argument of a point, so that should be open circle where they meet in the axis. Okay, so what I need to understand, why doesn't this go the full way around the circle? Okay, also, what is the centre? What is that value? I believe it's I. But I can't justify it. And then from that, what is the radius? Okay, so that's what I'm still working on in there. Because if this was pi on 2, this will be a semicircle, correct? If this was pi on 2. Because the angle in the semicircle is 90 degrees using your circle geometry theorem. You've got a circle, the diameter, okay, that's pi on 2, it'll form the diameter of the circle. So if this was pi on 2, therefore that would be the diameter, and you will get the locus of the semicircle. Okay, so what we need to get our heads around is when it's pi on 4, I'm thinking it might have something to do with this. So if that's pi on 4, this will become pi on 2. There, using your circle geometry theorem, but you've only got effectively that part of the arc. Thinking that's got something to do with it, but I'll have to have another query about it, unless you guys got some insights on how it would work. I'll be welcoming it. Say it again, sorry.
So we set the arguments as
Yeah.
PAX and then we just restated the question.
Restated?
Yeah, basically.
Oh, yeah, I did it that way so I can use my exterior angle result.
How's that supposed to prove anything?
How?
Yeah.
Can you prove something there?
Well, one thing would be if I can get the final parts of the question I'm still trying to get my head around, that might answer your question there as well. Okay? But the idea is that the difference between those two arguments at those 2 points is always pi on 4. Okay, so that means this angle here, using your exterior angle result, okay, must always be pi on 4. Okay? So, if that's the case, for these to be fixed and that angle to be fixed, this must, you really have to understand what's going on. It must produce a circular arc for it to stay.